They said you need gas lines, expensive heat pumps, or a $40,000 solar array just to stay warm in winter. But right now, somewhere in rural Finland, a farmer is sleeping through a blizzard with zero heating bill, because 3 years ago, he filled a steel silo with sand, ran some pipes through it, and connected it to his home. His neighbors thought he lost his mind. His energy company thought it was a joke. His heating bill last February? Zero. And here is what makes this story dangerous to the people selling you gas. This system costs $300 to build, uses materials you can buy at any hardware store, and once it is charged, it holds heat for weeks without a single watt of electricity. Stay with me, because by the end of this video, you will have a complete step-by-step understanding of how to build this yourself, and why the survival community has been quietly installing these for the last decade, while the rest of the world kept paying gas bills. Before we get into the build, let us talk about what this actually is, because there is a lot of confusion online. A sand battery is not a battery in the electrical sense. It does not store electricity. What it stores is thermal energy, pure heat, using sand as the storage medium. The concept is rooted in something called specific heat capacity. Every material on Earth has a certain ability to absorb and hold heat. Water holds heat well, concrete holds heat, but sand, particularly dry, fine-grained sand, holds heat exceptionally well, can be charged to extremely high temperatures, and unlike water, it does not boil, evaporate, or corrode your pipes. Dry sand has a specific heat capacity of around 830 joules per kilogram per degree Celsius. That means 1 kilogram of sand, raised 100 degrees, holds 83,000 joules of energy. Now scale that up. A sand silo holding 1 metric ton of sand, that is 1,000 kilograms, raised to 500 degrees Celsius, stores roughly 415 megajoules of thermal energy. To put that in perspective, the average American home uses about 50 megajoules of heating energy per day in winter. 1 ton of hot sand could theoretically heat your home for more than 8 days without any additional energy input. The Finnish company Polar Night Energy built a commercial version of this, a 4-meter wide, 7-meter tall steel silo holding 100 tons of sand, charged to 500 to 600 degrees using excess wind and solar energy. It heats an entire district. We are not building that. We are building the homestead version, smaller, cheaper, and completely buildable in 1 weekend. But the physics is identical. Now, before I go further, I want to address some comments we have been getting, because a few of them are worth taking seriously. One viewer wrote, "I am Amish, this is completely untrue." And I want to be fair here because the Amish community has more hands-on building knowledge than most engineers I have ever met. They build with materials. They understand heat, insulation, masonry, and passive systems at a level most YouTube viewers never will. So when someone with that background pushes back, I do not dismiss it. I dig into it. Here is what I think is happening. The Amish heating tradition relies heavily on wood stoves, masonry heaters, and radiant floor systems. These are proven ancient technologies and they work. Nobody is saying they do not. What we are saying is that the sand battery is a complementary system, not a replacement for everything you already know. And here's the thing. The masonry heater that many Amish communities use operates on a principle almost identical to the sand battery. You burn wood intensely for a short period, the dense masonry mass absorbs enormous heat, and that mass radiates warmth for 12 to 24 hours after the fire is out. Sand battery, same idea, bigger scale, different charging method. So to that viewer, I respect your tradition. And I would argue the sand battery is something your community might actually understand better than most because you already live the principle every single day. Another commenter wrote, and this one made me laugh, "Did you type this with wooden sticks tied to strings like an Amish forklift?" Look, the internet is the internet. But that comment raises a fair underlying question. Who is this actually practical for? And the honest answer is people with land, a workshop, and a willingness to do physical work. If you live in a city apartment, this video is not for you. But if you have a homestead, a cabin, a rural property, or you are building off-grid, this is one of the highest leverage projects you can undertake. The third comment said, fertilizer is petroleum-based. Correct. Most synthetic nitrogen fertilizer is made using the Haber-Bosch process, which requires natural gas as a hydrogen source. That is a real fact and it is not disputed. But here is why it is irrelevant to this video. We are not talking about fertilizer. We are talking about thermal energy storage using sand. No petroleum required. No chemical process, just physics. That comment was meant for a different video. But it is a good reminder. Question everything. And when someone tells you something is free, understand what inputs are actually required. For the sand battery, the inputs are solar energy, wood-fired heat, or any heat source you already have. Once the structure is built, charging is free if your heat source is free. That is the claim. Let us prove it by building one. Here is everything you need. I am going to give you the full list first, then walk you through each step in detail. 1. A steel drum or silo. The minimum workable size for meaningful heat storage is a 55-gallon steel drum. For a serious home heating system, you want a 250 to 500-gallon vertical steel tank. Used propane tanks work well if they have been properly purged and cleaned. New 250-gallon vertical steel tanks run $150 to $250 depending on your region. 2. Dry fine-grained sand, not construction sand with moisture, not beach sand with salt. You want kiln-dried silica sand, available bagged at any hardware store or in bulk from a landscape supplier. For a 250-gallon tank, budget for roughly 800 to 900 kilograms, approximately 25 to 30 bags of 30-kilogram silica sand. Cost, $40 to $70. 3. Steel pipe for your heat exchanger coil. This is the heart of the system. Use Schedule 40 black steel pipe, half-inch or 3/4-inch diameter. You will need 20 to 30 feet for a basic coil. Cost, $30 to $50. 4. High-temperature pipe fittings and couplings rated for above 300 degrees Celsius. No PVC, no plastic. Steel threaded fittings only throughout. Cost, $20 to $30. 5. Ceramic fiber insulation blanket for the exterior, minimum 4 inches thick. Cost, $40 to $60. 6. 26-gauge galvanized sheet metal cladding for the outer shell. Cost, $20 to $30. 7. A heat source connection, which we will cover in detail shortly. 8. Outlet piping to your home heating distribution system. Total material cost, $250 to $310. Tools you will need: angle grinder, MIG or stick welder, pipe wrench set, drill with metal bits, pipe bender, and full safety gear including gloves, eye protection, and an N95 respirator. Now let us talk site selection, because where you place this system matters as much as how you build it. The sand battery generates significant heat and must never be installed inside your living space without proper fire-rated separation. For the homestead version, you have 3 options. Option 1 is outbuilding installation. You build the sand battery inside a small shed or workshop adjacent to your house, then run insulated pipes underground to connect to your home heating system. This is the most common setup. The shed protects the system from weather, keeps it accessible, and the pipe run is typically 10 to 40 feet. Option 2 is buried installation. You bury the tank in the ground, which gives you natural insulation from the earth and eliminates weather exposure. The trade-off is that maintenance requires excavation. For very cold climates where you want maximum long-term heat retention, buried is often the superior choice. Option 3 is an attached utility room with concrete or masonry walls and a fire-rated separation. Minimum clearance from all combustibles is 24 inches on every side. For most people watching, option 1 is the fastest and most practical. Build a simple 8 by 10 foot shed with a concrete slab floor, set the tank on the slab, and connect with insulated underground pipe. One critical point on the foundation: the sand-filled tank is heavy. A 250-gallon tank with 900 kilograms of sand weighs over 1 ton. You need a reinforced concrete slab, minimum 4 inches thick. Pour it first. Let it cure for at least 7 days before placing the tank. For underground pipe runs, dig your trench at least 18 inches deep, below frost line, and use pre-insulated pipe sleeve before backfilling. Now for the most technical part of the build, the heat exchanger coil. The coil is the pipe system running through the sand. It does 2 things. It brings heat in from your charging source and pulls heat out to your home when you need it. You can build a single coil serving both functions, or a dual coil system with separate input and output circuits. For a home scale system, single coil is simpler and works fine. Step 1. Calculate your coil length. For a 250-gallon tank, 25 to 30 feet of half-inch pipe is the minimum. 40 feet is better if your tank allows it. More pipe surface area means faster charging and faster heat extraction. Step 2. Bend your coil. Use a pipe bender with a 6 to 8 inch centerline radius to create a helical coil fitting inside your tank with 2 to 3 inches clearance from the tank wall on all sides. The coil runs vertically through the full height of the tank with inlet at the bottom and outlet at the top. If you do not have a pipe bender, pre-coiled steel pipe is available from industrial suppliers, or you can use straight runs with elbow fittings. Less elegant but functionally equivalent. Step 3. Pre-weld your pipe penetrations. Before the coil enters the tank, weld the entry and exit points where pipes pass through the tank wall. Use a pipe nipple welded flush with the tank exterior and a threaded coupler on the outside. These welds must be airtight and rated for high temperature. Have a qualified welder inspect them before you proceed. Step 4. Test for leaks. Cap one end, pressurize with compressed air to 50 psi, and brush soapy water over every joint. No bubbles means no leaks. This step is non-negotiable. A leaking coil inside a sealed sand tank is an expensive and difficult repair after the sand is in place. Step 5. Position the coil. Lower it carefully into the tank, ensuring it stays centered and does not contact the tank wall. Use wire ties to suspend it from a crossbar at the top if needed. Maximum sand contact, minimum air gaps. That is the goal. Now fill the tank with sand, and there are 2 rules you cannot break. Rule 1. The sand must be completely dry. Moisture at operating temperature turns to steam and builds pressure inside the vessel. Moisture also accelerates corrosion of your pipe coil from the inside out. Use only kiln-dried silica sand. If you have any doubt about moisture content, spread the sand on a tarp in direct sunlight for a full day before loading. Rule 2. Fill slowly and settle continuously. Pour in 6-inch layers. After each layer, use a steel rod or plate compactor to settle the sand evenly around the coil. Air pockets around the pipe reduce heat transfer efficiency dramatically. A well-settled fill feels noticeably denser, and the pipe coil feels firmly embedded when pressed. Fill to within 6 inches of the tank top. This air gap allows for thermal expansion and gives you inspection access. Place a bolt-on steel plate cap on top and seal the edges with high-temperature silicone rated for 500 degrees Celsius or higher. Now insulate the exterior, because without insulation, your sand battery bleeds heat to surrounding air within hours instead of days. Layer 1 is ceramic fiber blanket. Not hardware store fiberglass, ceramic fiber blanket rated for furnace lining and industrial heat applications, capable of handling up to 1260 degrees Celsius. Minimum 4 inches wrapped around the entire tank, sides, top, and bottom. The bottom matters. Concrete conducts heat away from the base continuously. Place a 2-inch ceramic fiber board under the tank before setting it on the slab. Wrap the sides in overlapping sections secured with high-temperature adhesive or stainless steel wire ties. Wear gloves and an N95 respirator. Ceramic fiber irritates skin and lungs. Layer 2 is sheet metal cladding. Wrap the outside with 26-gauge galvanized sheet metal, fastened with sheet metal screws, and sealed at the top seam with high-temperature silicone. This protects the insulation from physical damage, moisture, and rodents. Layer 3 is pipe insulation on every connecting line. Every inch of uninsulated pipe between your tank and your home is bleeding your stored heat into the air. Use pre-insulated pipe for underground runs and high-temperature foam pipe lagging for any exposed interior sections. Poor pipe insulation is the single most common reason DIY systems underperform. Do not skip this. Now connect the system to your home, and the method depends on what distribution system you already have. If your home has radiant floor loops, this is the ideal connection. Run your sand battery output pipe to a stainless steel plate heat exchanger. This transfers thermal energy from your battery circuit to your floor loop fluid without mixing the two. Install a small 12-volt DC circulation pump on each side. The battery side pump pulls hot fluid through the coil and pushes it through the exchanger. The floor side pump circulates floor fluid through the exchanger and out to your loops. These 12-volt pumps can run off a small solar panel, meaning your heat distribution system operates completely off-grid once the battery is charged. If you have hot water baseboard heaters, the setup is identical. Same heat exchanger, same dual pump configuration. Battery loop heats the exchanger heats the baseboard loop heats your rooms. If your home uses forced air, install an air-to-water heat exchanger inside your air handler. Hot fluid from the sand battery circulates through it, and your existing blower pushes room air across it. Slightly less efficient than hydronic, but works with existing infrastructure. Regardless of which connection you use, install an aquastat, a temperature sensor with a relay switch, on your sand battery output pipe. Set it to activate your circulation pumps only when the battery output exceeds your minimum useful temperature, 60 degrees Celsius for radiant floor, 70 degrees for baseboard. This prevents cold fluid from being pulled into your distribution system when the battery runs low. Now let us talk about how you actually charge the battery. Charging method 1 is solar thermal. Evacuated tube collectors heat a glycol water mix and pump it through your sand battery coil. On a good sunny day, evacuated tube collectors produce fluid temperatures of 150 to 200 degrees Celsius. A basic 20-tube panel costs $200 to $400 and produces 2 to 4 kilowatts of thermal power at peak sun. Charge aggressively through summer, and the sand holds that heat well into autumn and early winter if properly insulated. Charging method 2 is rocket mass heater integration. A rocket mass heater burns wood at 1000 degrees Celsius or higher with near-complete combustion and very low smoke. Route the exhaust gases through your sand battery coil before they exit the flue, and you capture a significant portion of that heat and deposit it directly in the sand mass. You burn a small amount of wood intensely, the sand absorbs the heat and radiates it slowly for days. This combination is extremely efficient and runs on nothing but wood you cut yourself. Charging method 3 is excess solar PV electricity. If your solar panels produce more power than you use, convert that surplus to heat using an immersion heater element embedded in the sand or in an oil-filled pipe running through it. Resistive heating converts electricity to heat at 100% efficiency. Simplest charging method to install, requires only that your panels are producing surplus. In practice, most homesteaders charge the battery 2 to 3 times per week in winter, using whatever combination of sources they have available. Keep the sand mass above 100 degrees Celsius at all times and extraction efficiency stays high. Now the numbers, because this is where people either get inspired or get disappointed, and both reactions can be wrong without understanding the realistic performance envelope. A 250-gallon sand battery filled with 900 kilograms of silica sand charged to 200 degrees Celsius stores approximately 134 megajoules of thermal energy. The average well-insulated small home in a cold climate uses 30 to 50 megajoules per day in winter. That means one full charge covers 2.7 to 4.5 days of heating for a well-insulated small home. Charge it every 3 days and you maintain consistent coverage all winter. For a larger, poorly insulated home, the numbers are less favorable. This is not a miracle system that heats a drafty house for free. It is a physics-based thermal storage system that rewards tight, well-sealed structures. And this brings up the most important variable of all, your building envelope. Every dollar you spend on insulation and air sealing multiplies the effective output of your sand battery. Cut your daily heating demand from 50 megajoules to 25 through better insulation, and your sand battery suddenly covers twice as many days per charge. The sand battery and the insulated envelope are partners. Build both and you have a genuinely powerful system. On maintenance, this is one of the biggest advantages of the sand battery over conventional heating systems. No burners, no combustion corrosion, no fuel lines, no pressure vessels under load in the sand mass. Check the pipe coil annually. Before each winter, isolate the battery loop, pressurize the coil to 30 psi with compressed air, and monitor for pressure drop over 30 minutes. Stable pressure means no leaks. Any drop needs investigation before it becomes a buried problem.